My name is Michael Pendezis, and this is Math 241, Probability and Statistics. This is our first online lesson. We're going to continue with Chapter 4 in this lesson. Okay? The last lesson, we talked about Chapter 4 and discrete random variables and probability functions. That's the title of Chapter 4. And so we started with an introduction, and then we talked about discrete random variables. So we talked about the idea of a discrete random variable. It's this function here. It's this function that I wrote as a machine diagram here, where if you take the input of this function is the outcome of an experiment, it'll spit out a real number. And so a discrete random variable is a function where if the input is the outcome of an experiment, the output is a real number. It assigns a real number to each outcome of an experiment. Okay? And it's discrete because its sample space is discrete. But we'll talk more about that in this lesson. Okay? And this lesson, so we will finish the rest of 4.2. We'll finish our discussion on what a discrete random variable is. Then 4.3, we'll talk about probability functions. 4.4, we'll talk about probability histograms and bar charts. And in 4.5, we'll talk about several important discrete distributions. Okay. So let's get started. So let's start with definition 4.1. And so this is in 4.2, continuing section 4.2. Okay, so let capital S be a discrete sample space with probability set function, capital P. Let capital X be a function that assigns a real number to each sample point in a sample space X. X, capital X, is called a random variable. Okay, and X is a discrete random variable, including the word discrete here, is a discrete random variable because its sample space is discrete. Okay? And so here we're defining a random variable. Okay, so let capital S be a discrete sample space with probability set function capital P. Let capital X be a function that assigns a real number to each sample point in a sample space capital X. Capital X is a random variable. Capital X is a discrete random variable because its sample space is discrete. Okay? And so that's the definition of a discrete random variable. Okay? So if we have a sample point here, and we have the value of X here, and so let's say our experiment in this example is tossing 2 die. Okay, so each cube is a die, and the top value on each die The experiment is the results you get on the top face of each die after you roll 2 dice. Roll 2 dice. Roll 2 die. Okay. And so an outcome of this experiment is the value on the 2 faces of the die. The first component is the value at the top of the first die. The second component is the value at the top of the second die. And this notation is used to give order to the 2 numbers so you can differentiate between the first roll and the second roll. Okay, and so the value of x here is going to be 2. X is going to be the sum of the 2 rolls. Okay, so x is the sum of the 2 rolls. Okay, so here that's our value of x. If the first roll is a 1 and the second roll is a 2, 1 comma 2, that ordered pair would be a representation of the 1 outcome of that experiment. And the sum of the 2 rolls would be 3. And then if it's 1 comma 3, x would be 4. And you can continue in this way until you get the last one, ordering it this way, where the first roll is a 6 and the second roll is a 6. And the sum of the 2 rolls is then 12. Okay? And so this is an example of a discrete sample, a discrete random variable. If we look at this sample space, capital S, it's discrete. There were 36 outcomes in this experiment. Okay, and so the size of the set S is 36. There are 36 total outcomes in this experiment. And so since the sample space is finite, it's discrete. If the sample space could be ordered as an infinite list, that could also be a discrete set. And so finite or an infinite list would be a discrete set. Okay. So here S is discrete, and we have a discrete random variable. We're assigning to each simple outcome a real number. And so X here is our discrete random variable. Okay, and so this is figure 4.1. Okay, let's go to example 1.2. Okay, so example 4.2. We're going to flip 3 coins. Okay, and the outcomes are either heads or tails. Those are 2 outcomes of flipping a coin, heads or tails, and we're going to flip 3 coins. Okay, and so we're going to use tables to find the following random variables. Okay? So for part A, capital X is the number of heads in the 3 flips. And so our goal is to find a table to define this capital X. Okay? I'm going to let little h be heads and little t be tails. So those are 2 outcomes of each trial in the experiment. Each flip of a coin can be little h heads or little t tails. Okay? And so the table is going to do this. We're going to have in the first column a sample point. For each sample point, we're going to have a value of x. And then each next column is going to be value of y. Good. So these are all the possible simple outcomes of the experiment. Okay, so we have 8 simple outcomes in this experiment. There are 8 ways to flip a coin 3 times, right? So that's our sample space, capital S. It's discrete. This is one of the ways of being a discrete sample space is if it's finite. And so S is finite, and so it's a discrete sample space. Okay? X is the number of heads in 3 flips. There are 3 heads in this one outcome. It's 3, 2, 2, 1, 2, 1, 1, 0. And so that's the value of X for each simple outcome of this experiment. And the value of Y, sorry, I have to define the value of Y for you. Little b, part B is going to be Y is the number of heads minus the number of tails. Okay. So to find the value of Y, it's number of heads minus the number of tails. It's 3. So that's 2 heads minus 1 tail is 1. 2 heads minus 1 tail is 1. 1 heads minus 2 tails is -1. Then 2 heads minus 1 tail is 1. 1 head minus 2 tails is -1. 1 heads minus 2 tails is -1. 0 heads minus 3 tails is -3. And so in this next column, we see the value of Y, which is the number of heads minus tails in the experiment. Oops. Okay. Okay, and so this table is now defining the random variable X and the random variable Y, right? They're both functions, and a function can be described using a table. And so this table is defining 2 functions, 2 random variables, discrete random variables. Okay, and so that's the end of 4.2. And so the homework for this section is going to be page 105 to 106, numbers 1 and 3. Okay. Okay, so make a note of that homework. And we're going to keep going. The homework will also be posted online, so you can see there. I also printed out the homework sheet for you being in the semester, but it's good to see it here because then you can see, where at what point in the semester should you be doing this homework. Great. Okay. So 4.3. Let's talk about 4.3. Good. It's probability. Okay, so 4.3 is on probability functions. Okay. And so the idea of a probability function is, first, if we think about what we were doing in the last section, was we had a discrete random variable, which we called X, sometimes Y. And the input was the outcome of an experiment. And the output was a real number. Right? So this was our discrete random variable, a function that assigned a real number to each outcome of an experiment. Now, what we want to talk about in 4.3 are probability functions. So what that's going to do is going to take all the possible values of our random variable, and it's going to tell us the probability of getting that number. And so the output here is going to be the probability of that real number. Okay? And so this is going to be our probability function, little f. Okay? And so today's discussion on this discussion of probability functions in this section is going to be a discussion about these functions, where we look at all the possible values of a real variable, and if we input them into this function, the outputs are the probabilities of our random variable being those possible real numbers. Okay, so we're going to study this function here. Okay, so an example 3, we consider 3 flips of a coin. Okay. And I'm going to let capital X equal the number of heads in the 3 flips. Okay. The possible values of X are 0, 1, 2, or 3. Right? So if you flip a coin 3 times, the number of possible heads are 0, 1, 2, or 3. Okay. So what we want to do is we're going to find the probability. Find the probability that a random variable X is equal to 0, the probability that a random variable X is equal to 1, the probability that a random variable X is equal to 2, the probability that a random variable X is equal to 3, right? The possible number of heads are 0, 1, 2, or 3. And so what is the probability that there are 0 heads, 1 head, 2 heads, or 3 heads? So that's the goal. Okay. And so if we look at the probability that X is equal to 3, that there are 3 heads, in our table, which I'm going to have to write again, we're going to have our sample points here, our outcomes and values of X. So heads, 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 tails, heads, tails, heads, heads, tails, heads. Okay, so we have these 8. These are the 8 outcomes of flipping a coin 3 times. X is the number of heads. So again, 3, 2, 2, 1, 2, 1, 1, 0. And so the probability that X is 3, the probability that the value is 3 is the probability that we get only that outcome in the experiment. Well, each of these 8 outcomes are equally likely. So the probability of getting this 1 out of the 8 equally likely outcomes is 1/8. Use 0.125. Okay. But you might want to think of the fractions to learn it. Okay. Probability that X is equal to 2, that's the probability that exactly 2 of them are heads. Right? There's those 3 outcomes of the experiment. We have this one, and that one. There's exactly 3 out of the total 8 equally likely outcomes where there are 2 heads, or X equals 2. And so there's a 3/8 chance of X equaling 2, and that's 0.375. Okay. Now the probability that X is equal to 3 is the probability that the outcome of your experiment has 3 heads. Has 3 heads. Has 1 head. And so the probability of having 1 head is just the probability of one of these 3 guys happening with the squiggly circle. This one, for that. So there's 3 out of the total 8 where there's exactly 1 head. And will later equally likely. So it's a 3/8 chance, which is 0.375. And so the probability that X equals 1 is 0.375. Now the probability that X is equal to 0, that's just, there's only 1 outcome of the experiment where there are 0 heads, and it's 1 out of the total 8. And that's 0.125. And so the probabilities of 0 heads is 0.125, probably X equals 1, and so forth. Okay. And our intuition should tell us that the sum of all these probabilities should be 1. And it is. 1/8 plus 3/8 plus 3/8 plus 1/8 is 8/8, and that's 1. Okay, and so this looks right. Okay, so we've now found the probability that X equals 0, probability X equals 1, probability X equals 2, and probability X equals 3, and so now I'm checking to make sure I answered the entire question, which I did. Okay, so this is an example of a probability function, where the inputs are all the values of our discrete random variable, and the outputs of each possible value is the probability of your random variable obtaining that value. Okay, so that's how that example, this example is an example of a probability function. Okay, so now definition 4.2, let capital X be a discrete random variable defined on a sample space capital S with probability set function capital P. The probability function of probability distribution X is the function little f defined by little f of x. F of little x is equal to probability of capital X is equal to little x for each possible value. Little x or discrete variable capital X. Okay, and so in definition 4.2, this is the definition of a probability function. Okay, so the probability function of a probability distribution X. Right, this guy. Okay, so with that definition, let's see examples of it. We'll do some math, and it will make more sense. This definition is saying what we can do with the definition. Okay, so example 4.4, we're going to roll 2 dice. X is the sum of the 2 values on the top face of each die. And so part A, we're going to find the probability function of capital X. Okay, so we're going to find the probability function of capital X. So that's just this table. Little x is the sum of the 2 values, right? And so there's 2 dice. One die, a second die. It could be a little different size. Right, in the top face we record in each one, and we take the sum, right? So x is the sum of the top values of the 2 die. Each die ranges in values from 1 to 6. Well, then the smallest sum could be 2. 1 plus 1 is 2. And the largest value could be 6 plus 6 is 12. And then everything in between you can get. Okay? So the sum can range from 2 to 12, including 2 and 12. 1 plus 1 is 2, 6 plus 6 is 12. And so if you think of all the possible outcomes of rolling 2 die, there's 6 outcomes here and 6 here. There's 36 possible outcomes of the experiment. There's 36 outcomes of rolling 2 die. Okay? And each of those 36 is a value of x. Okay? And so if you looked at what the probability of a sum of 2 being, it would be 1 out of 36, because there's 36 total outcomes in the experiment. There's only 1 comma 1. There's only 1 out of 36 equally likely outcomes, where the sum is 2. So it's 1 out of 36. 3 is 2 out of 36. 4, that's 3 out of 36, 5, 4 out of 36, 6, 5 out of 36, 7, 6 out of 36, 8, 5 out of 36, 9, 4 out of 36, 10, 3 out of 36, 11, 2 out of 36, 12, 1 out of 36. Okay? So I'm just writing that down, showing you an example. So for each possible value of your discrete random variable, we assign to it, we find the probability that capital X is equal to one of any of its possible values. Okay? And so this is figure 4.8. And so this is the probability function of X. So you're used to seeing a function described as an equation, but that's only one way to describe a function. We can also describe a function as a table. And so this table is us saying what the function rho f is. And it's a probability function of this discrete random variable, capital X. Okay. Okay, so in part A, we found the probability function of capital X. And so I'm going to erase this one. Okay, so now for part B, we're going to find the probability of a sum of 7 or 11. Okay, and same experiment, same probability function, same discrete random variable. So the probability of a sum of 7 or 11 is the union of two mutually exclusive events. You can say event A is the event of a sum of 7, and event B is the sum of 11. These are two disjoint events. Their intersection is empty. You can't have an outcome of an experiment of having both the sum of 7 and 11 at the same time. So these are two mutually exclusive events. And so the sum of 7 and 11 is the probability of A union B. And we know that the probability of a union of mutually exclusive events is the sum of their respective probabilities. And so we know this equation holds. And that's because we have that A and B are mutually exclusive. So A and B are mutually exclusive events, and so the probability of the union is the sum of their respective probabilities. And so we're going to use this fact and say that this is the probability of the sum of 7 plus the probability of the sum of 11. Makes sense? But X is the sum of the two values. So capital X is the value of the sum. And so this is the probability that X is equal to 7 plus the probability that X is equal to 11. Make sense? And then this is equal to the probability that X equals 7. The probability that X has a value of 7 is 6 over 36. Plus the probability X is 11. That's 2 over 36. This is 8 over 36, and that's 2 ninths. In simplest form. And so in B, we find the probability of the sum of 7 and 11 to be 2 ninths. Okay. So now in part C, we're going to use this table again. And now in C, we're going to find the probability that the sum is greater than 8. Okay, so we'll find the probability the sum is greater than 8. And so the probability of the sum is greater than 8 is equal to the probability the sum is equal to 9, or the sum is equal to 10, or the sum is equal to 11, or the sum is equal to 12. Right? Because the possible values of the sum are 2 through 12, but if it's greater than 8, it can only be 9, 10, 11, or 12. Okay. Well, this, and this, these are 4 mutually exclusive events. The intersection of any of these sets, any two of these sets, is empty. before. So these are mutually exclusive events, and so that means this is the probability of the union. So this is the same as the probability that x is equal to 9, or x is equal to 10, or x is equal to 11, or x is equal to 12, because the sum is x. So then this is the probability of a union of mutually exclusive events, and that's equal to the sum of their respective probabilities. This is the probability x equals 9, this is the probability x equals 10, plus the probability x equals 11, plus the probability of x is equal to 12. Okay, and then you just plug in the probabilities over here. So probability x is 9 is 4 out of 36, plus the probability x equals 10 is 3 out of 36. Plus the probability x is equal to 11, which is 2 out of 36. Plus the probability x equals 12 is 1 out of 36. And so if you add up those probabilities, you get 10 out of 36, which is 5/18. And so 5/18 is the probability that the sum is greater than 8. Okay. So that's part C. And then part D, and in part D, we want to find the probability that the sum is greater than 3, but less than 9. So probably the sum is greater than 3, but less than 9. So the probability that the sum is greater than 3, but less than 9 is equal to the probability that 3 is less than the sum, strictly less than 9. And that's equal to the probability x is equal to the sum, which is x is equal to 4, or x is equal to 5, or x is equal to 6, or x is equal to 7, or x is equal to 8. And these are mutually exclusive events. These 5 events are mutually exclusive. So this is equal to the sum of those respective probabilities. Okay. And so what is the probability that x equals 4? It's 3 out of 36. What's the probability that x equals 5? It's 4 out of 36. Plus the probability x equals 6 is 5 out of 36. Plus the probability x equals 7, which is 6 out of 36. Plus the probability x equals 8, which is 5 out of 36. So you add up these and you get 3, 4, 7, 12, 18, 23 over 36. Okay, so find the probability the sum is greater than 3 but less than 9 is 23 over 36. And so that's example 4.4, parts A through D. Okay, so in theorem 4.1, let f of x be the probability function of a discrete random variable, capital X. Then a 0 is less or equal to f of x, less or equal to 1 for every possible value little x of capital X. And part B, the summation of the little x of f of x is equal to 1. And these x's, the summation over all possible values little x of capital X, random variable capital X. Okay, and And so this is theorem 4.1. So let f of x be the probability function of a discrete random variable capital X. Then the probability f of x is between 0 and 1 inclusive. And the sum of all of the f of x's is 1, just like you would suspect. Okay, and the summation is over all possible values little x of capital X. So you're only considering little x that are values of your discrete variable for both of them. Okay, and so that's the end of 4.3. Okay, and so the homework for 4.3 is pages 109 to 110, and their exercises number 3, 6, and 9. Okay, and so that's the homework for 4.3. Okay, done with 4.3. Next is 4.4. So 4.4, and 4.4 is on probability histograms. And bar charts. Okay. So this is an example of a probability histogram. And so it'll be easy enough to see in the example. So let's just take a look at this example. Okay, so these are all the possible sums of 2 dice rolls. The experiment is rolling 2 dice. Right, and you have the top value on each die. And so our random variable capital X is the sum of the 2 values on the top side of each die. We roll 2 dice. Okay, and X is the sum. Okay, and so the possible values of the sum range from 2 through 12, just like we talked about before. And we're going to describe a probability function of little f of x. And we're just going to say in this histogram, probability histogram, what the probability is of x attaining all of its possible values. And so those possible probabilities we found were 1 over 36, 2 over 36, 3 over 36, 4 over 36, 5 over 36, and 6 out of 36. Right? So those are all the possible values of a probability function. And so this is the probability histogram. Of it. All right, so that's the probability. That's the probability histogram. It's describing our probability function f of x in this way, right? So let's say you want to know what the probability that the sum was 7, 2 dice rolls. Probability it was 7 is 6 over 36. Probability the sum is 11 is 2 over 36, and so this is describing for you the function to the left of x. And so nothing is lost in this histogram description. We're saying everything we need to know in order to know exactly what function to the left of x is. Okay, and so this is an example of a probability histogram. Okay, so that's a probability histogram where the experiment is rolling 2 dice and the discrete random variable is the sum of the values on the top side of the 2 die. Okay. Okay. And so that's figure 4.4. Okay, that's figure 4.4. That's a probability histogram. Now in figure 4.5, we're going to have a bar chart. So, same experiment, same discrete random variable. We're just going to express it using a bar chart, which is very similar to the sum of two dice rolls. Same experiment, we roll two dice. Take the top value in each die, capital X is the sum of the two dice rolls, and the possible values of X range from 2 to 12. Those are the possible values, right? So two dice rolls. Our function, little f of X, the values are here. This is a bar chart of a probability function. So this bar chart is describing the same probability function. The probabilities range from 1 over 36 to 6 over 36. Okay, so all 1 over 36 to 6 over 36, those are the possible values of this probability function. And so the bar chart will just be a bar, which in this case, if you do it as a line, it's just a thin bar. Okay, so here the bar chart is describing the same probability function, but it's doing it as a bar chart. This is a bar chart of this probability function after little f of x. Okay, and this is figure 4.5 in the book. So figure 4.5 in the book is a bar chart of the probability function. Okay, and so now you see what a probability histogram is and what a probability bar chart is. Okay, and that's the end of 4.4. 4.4 is really short. And the homework for this section is page 111. And numbers, just number 2. And so that's the homework for 4.4. Okay, 4.5 is going to have several importance. Discrete distributions. Okay. And so in the first section of 4.5, 4.5.1, we're going to talk about the discrete uniform distribution. Okay, so we're going to describe generally what a discrete uniform distribution is. So the experiment, I'm going to try this more visually. I'm just writing out definition. Let's say our experiment is selecting a number at random from the set x1, x2, xn, right? So the 1 to n means there's n distinct numbers in the set. These are distinct, okay? So we're selecting a number at random from a set of n distinct numbers. Right? So these could be anything, any n numbers as long as they're distinct. Capital X is the number, is the value of the number selected. Okay. Our assumption in this experiment is that each of the x1 to xn are equally likely selected. Okay, so we're assuming that every number in that set is equally likely to be chosen. Okay, then what we're saying is that the f of little x sub I is equal to the probability that the value of capital X is equal to x sub I, and that's 1 over n. And that's for values for I equal 1 to n. Okay? And so what this is saying is that the probability that you choose any of these n equally likely distinct numbers is 1 over n, which makes complete sense because each of these numbers is one out of the total n distinct numbers in the set that are equally likely to happen by our assumption. So f of x sub I is 1 over n for I equals 1 to n. And this is a general description of a discrete uniform distribution. And so this set could be any n things, and each of their probabilities is the same. And so then you would define the probability of selecting any one of them to be 1 over n for any n. Okay, and so this is called the discrete uniform probability function. Okay, so this f is a discrete uniform probability function. Okay. Okay, so that's called discrete uniform probability function. And so to make this, just to sum this up, definition 4.3 is that definition. The function f of x sub I is equal to 1 over n for positive integers little n such that I equals 1 to n is the discrete uniform probability function. Okay, so that's just saying that. So that's the definition of this discrete uniform probability function. Okay, and so to add just one note to that, I'm going to put it here so I can include it in this board as a note, a random variable x has a discrete uniform distribution. And is a discrete uniform random variable if its probability function is a discrete uniform probability function. Okay. So this is the note at the end of this. Okay, so if the probability function is this, the discrete uniform probability function, then your random variable x has a discrete uniform distribution and is a discrete uniform random variable. Normally the x's we've been talking about are discrete random variables, right? But if you have this function defined on x, it's now a discrete uniform random variable. You add the word uniform here. In addition to the original variable we were talking about, you add the word uniform here if you get this probability function to find out. Okay. Okay. And so that is one example of an important discrete distribution. The second one in 4.5.2 is the Bernoulli distribution. Okay, so it's a Bernoulli distribution. Okay, and so to explain this, we're going to do it more visually. Okay? So our experiment has two possible outcomes. Outcomes are success or failure. Okay, those are our two outcomes in our experiment, success or failure. And this is called a Bernoulli trial. Okay, so an experiment is made up of Bernoulli trials, where each trial has only two options, success or failure. Okay. And so here a random variable assigns to success the value of 1, and assigns to failure value of 0. And so the two outcomes are success or failure in a Bernoulli trial. And our random variable assigns the real number 1 to a success and the real number of 0 to a failure. Okay? And this is called a Bernoulli random variable. Okay, so this is our Bernoulli random variable, and our Bernoulli trial is when the outcomes are success or failure. Okay? Our Bernoulli random variable is our x that assigns 1 to success and 0 to failure. Okay. So now, if the probability, if little p is the probability of success, q, which is 1 minus p, is the probability of failure, then f of x, our probability function, is p if x is 1, and q if x is 0, right? So our random variable is 1 if we succeed. That has a probability of p, little p, and we fail if x is 0. And so if x is 0, the probability that x is 0 is little q, is the probability of failure. Okay. And so this is our conclusion. And so this is our probability function. And so this probability function is called the Bernoulli probability function / distribution. So our Bernoulli probability distribution function is this guy. You could also call it Bernoulli probability distribution. Replace function with distribution. Okay, FCN is abbreviation for function. Okay, so that will of x is a function. Okay. And so definition 1.4 is just summing it up. And it says the function little f of x, which is equal to little p if x is 1, little p if x is 0, where little p is between 0 and 1, and p plus q is equal to 1, is called the Bernoulli probability function. Okay, so that function, f of x, where 0 is less than p less than 1 and p plus q is 1, is called the Bernoulli probability function. Okay. And so now that's the Bernoulli distribution. So in this example, I'm going to consider n Bernoulli trials. Each trial is success or failure, right? So we consider n of those trials with success or failure. If S of n is the number of successes in the n Bernoulli trials, right? And what is the probability function? The question is, what is the probability of S of n equal to little x for x equals 0, 1, 2, up including little n. Right? There are n Bernoulli trials. There are little n Bernoulli trials. And so each trial is success or failure. So if you're doing n Bernoulli trials, the number of successes range from 0 to n. From 0 to n. You either succeed none of them, succeed all of them, or somewhere in between. Okay, so we want to find this probability function. P of S of n is equal to x, for x from 0 to n. Okay, I'm going to let solution. We'll let S sub I equal to the event of success in the ith Bernoulli trial. So for instance, S of 1 would be success in the first trial, S of 3 would be success in the third trial. And then similarly, F sub I is the event of failure in the ith Bernoulli trial. So F sub I is the event of failure in the ith Bernoulli trial. Okay, so the probability of S1, S2, dot, 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 S of x, F sub x plus 1, F sub x plus 2, dot, 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 F sub n. Let's find that. So step 1 is we want to find the probability that the first S, or the first x are successes, and then the last n minus x are failure. So the first x trials, and the last n minus x trials. Right, so there's a total of n trials, and so if the first x trials are success, and then the last n minus x trials are failure, then the total, those are the total n trials, right? We have n Bernoulli trials. And so we're going to find the probability that the first x are successes and the last n minus x are failures in these n Bernoulli trials. And so these events are independent events. They're all independent events. And so that means that this is the product of their respective probabilities. Okay. So there's x of these. And there's, again, n minus x of these. And so that means that each of these has a probability of p, and each of these has a probability of q. But the probability of success is p, and the probability of failure is q. So I'm multiplying p by itself x times, and I'm multiplying q by itself n minus x times. And so that is the probability that the first x trials are success, and the last n minus x trials are failure. P of the x times q to the n minus x. Okay? So there are n choose x number of ways to choose x of the n trials to be successes. Right? So we showed that if the first x trials are successes and the next n minus x trials are failures, for that particular ordering, this is the probability. But if we rearrange the order of the successes and failures, that would still account for x, the same number of successes and the same number of failures. And so for each reordering, we have to consider this probability of that ordering. And so how many ways we can order them is how many times we have to multiply this by to find the probability of x successes and n minus x failures. So there are n choose x number of ways to choose x of n trials to be successes. So the probability that our random variable capital X is equal, or S of n is equal to x, that the number of successes in n Bernoulli trials is some fixed little x, is the probability that x are successes and n minus x are failures. So for any particular arrangement, that's the probability of p dx times q n minus x, and then you multiply it by n choose x, because that's how many of those you have to add to get the total probability. So this probability is equal to that. Okay? And this works for any value of x. So for x equals 0, 1, 2, up to including n. Because there are n trials, and so you could succeed at most n times, or this view is 0. Okay. And this function is called the probability density function. So that's a probability density function. Sorry, it is that, but specifically it's a binomial probability function. Okay, so that's a binomial probability function. The word binomial because there's two choices, success or failure. So binomial probability function. Okay, that would be specific. It's f of x, which is this, and so that this guy, middle f of x, which is the probability of s of n equals to middle x. Which is that. That's the binomial probability function, middle f of x. Okay, so that's an example of a binomial probability function. Okay, and so let's just define it. So definition 4.5, let u n be a positive integer. Let little p and little q be probabilities. With p plus q equal to 1. The function little b of x semicolon n comma little b is equal to n choose x with p to the x, q to the n minus x for x equals 0, 1, to including n is the binomial probability function. That's the definition of the binomial probability function. But in the last example, you can see an application of it, and it might make more sense. Okay, and so this function is dependent on how many successes, the number of trials, and the probability of success. And so in order to define this function, you need to know these three things, and that's why the input of this function is actually 3 inputs. So you need to know those 3 things to define this function for a particular problem. So that's why there's 3 inputs. Okay, and the semicolon is because these 2 things have to do with the experiment, where you take how many trials of the experiment is defined by a certain number of trials and the probability of success in each trial. And then this x is kind of just thinking, well, in that experiment here, how many successes are we talking about? What's the probability of what you want to know is you're thinking of a certain number of successes there. Okay, so the n and p have to do to find the experiment, and the x is what do you want to know about that experiment from this function. Okay. One note is that a random variable has a binomial and is referred to as a binomial random variable. If its probability function is the probability, is the binomial probability function. Okay, so if the probability function is this binomial probability function, then you have a random variable with binomial distribution, and it's called a binomial random variable. If your probability function is this. Okay. And the second note is that the b of x semicolon n comma p is equal to b of n minus x and 1 minus p. And so what does that mean? Well, first, this thing is the probability of x successes, right? If you have n trials, this is what the chances are that x of them will be successes. Well, that's the same as with the same number of trials. Instead of x successes, it's n minus x failures, right? P is the probability of success. 1 minus p is the probability of failure. This is q. And so the problem is finding that the probability that x of them are successes is equal to the probability of the rest of them being failures. Same thing. Okay, equal. Okay, and so that's defining the probability, the binomial probability function. Okay, and so next class we will look at examples of the binomial probability function. That will be lesson 2 online. Okay, so make sure to keep watching these videos, to read the announcements online, to answer my emails, read my emails, to do the homework assignments, and I'll have a separate, very short video explaining what will happen about test number 1. Okay, so watch that video too. Okay, thank you for attending, and see you soon.